Hi everyone, my name is Xin Rong. I'm a UIST doctoral candidate. I work with Eitan Adar too, and I'm going to talk about my work with my colleague Shiyan, Stephen, Mira, and Eitan. So this is a practice talk for the upcoming WIST, like Walter said. It's happening in Japan, Tokyo. And this work is about using neural net and user interface design to help people with better programming experience, improving their programming experience. So our motivation is that programming is not so easy, because one of the reasons is that programming often involves a lot of APIs that have a lot of complex functions and parameters, and also user does not always know how to translate a task in their mind to the actual code they're writing. So, among a lot of different programming paradigms, we're focusing on interactive so-called interactive programming practice. It's kind of the kind of programming that you do, like using MATLAB, R, Stata, a Python notebook, where you change some code, you immediately see the results, and you iterate, you change some more, and you see more results. That way you can quickly guide insights of the data or visualization, whatever you are manipulating. So, traditional solutions to solve these problems, traditionally people just go to Google or Stack Overflow like this, and there are also people in software engineering community that developed code search systems that help people to find code examples, or some machine learning work that have done like programming by example, or so-called natural language-based code synthesis. We think that among these work, there are some common problems. So all of these work, usually there is a system, and that system is usually unaware of what the user is actually thinking, what the user's task is actually, right? So the system unawareness of the user's current problem space prevented the system to suggesting more accurate results. The second common problem is that there usually lacks some support of mapping the model's output or the system's output back to the user interface, so that the user can use that output in a more fluid way, complete their task more quickly. So that hurts the user productivity overall. And we want to address these solutions. And I think there are several very great opportunities. And one of them, the biggest opportunity, is this recently rapidly developing field, which is deep learning. And the beauty of deep learning is that it is simple and crude, in the sense that it keeps human out of the so-called engineering loop, at least partially, right? And it can transfer what it's learned from task 1 to task 2 with very little cost. And more importantly, it is powerful that in the sense that you give it more data, and then you increase the complexity of the model by adding more layers, you get better performance. So luckily, we have a lot of data exactly to train that kind of model, and that data is everywhere on the web, right? We have Stack Overflow, GitHub, Bitbucket, all of these kind of things on the web. There are like tests, there are code, and there are associations between text and code. We can make use of them to help us train the deep learning model so that we support user experience. So deep learning model are all like black boxes, right? So designing deep learning method is kind of like designing a black box. All we want to do here is to design a black box that supports certain kind of input and produce certain kind of output. And the simplest case is some black box that takes natural language as input and produces code as output. That's the ideal scenario. And there's some also other scenarios where the user has already a piece of code, and he has something in mind that he wants to change the code, right? He can describe in natural language how I want to change the piece of code. And then the system can say, hey, this is how you change the code. So that's the overall idea. And here's what we have achieved in this paper. So we implement our system for Matplotlib. It is a kind of a common plotting programming library in the paradigm used a lot in so-called interactive programming. And I'm going to show you a video and showing like how the system works. And in the video, assume that the user has this kind of chart in mind, and he wants to create this chart from scratch by writing code. So let's see how the system works. So I'm going to load up the video. I can see. Oh, I can see. Wait. How do I mute this one? Awesome. So let's look at the video. So suppose the user wants to create a bar chart from scratch. So this is the system interface. It has a code editor, NL query bar, and some system function suggestions. The users can just type in the query, create a bar chart, and then the system automatically suggests what functions the user should use, and then the user can click on the suggested function. So what these are like the image examples generated by the code examples related to that function. So the user can pick whatever image he or she likes, and then the code example automatically populates into the code editor, and the corresponding image generated by the code is also automatically available for previewing. So that's like starting something from scratch. Now, what's the second step? Suppose the user wants to add a title here to the graph. So what does the user do? The user can say, type in a query, add title to the bar chart or the graph, and then the system automatically suggests the function that the user should use. The user can click on the function, and then it automatically lists a number of parameters the user should use. 0 means the first non-named argument, and the user can click on it and see a list of suggested values that are ranked based on how the code example, based on the counts in the actual code example is crawled from the web. So this, the user can pick anything like that one, and then click insert, and then the code is automatically changed, and the preview is also automatically available. So the third thing is, now suppose the user wants to change the color of these bars. So let's say the user type in, I think it's change the color of the bar. Change the color of the bar. And sorry. and the system should automatically highlight the line of code that she should change, and the user can click on the suggestion, click on the value, and then hit update. And then the code is automatically changed, and then the image preview is also automatically changed. So let's go back to our presentation. So let's recap what happened, what just happened. So what you have seen in the video are 3 scenarios. So scenario 1 is the user creates something from scratch, which is some NL as query to some black box, and it generates some code example. And scenario 2 is the user wants to insert a new line, or a set of new lines. And then the input is natural language and code context, and the black box generates new lines of code and where to insert that code in terms of code context. And the third scenario is the user wants to modify an existing code snippet. So the input is a code snippet and a natural language command, and the black box generates highlight the lines of code that she should change, and then actually suggest the suggestions. So how does this work? Well, it turns out that the 3 scenarios can be supported by one single black box. It takes input, it generates some output, and we need to, again, the beauty of deep learning is that as long as you have a lot of training data, you can train such a model, right? So, what's even better is that if you don't have a lot of pairs of natural language and code context, if you only have a lot of natural language, or if you only have a lot of code, you can still make use of them to further improve the performance of the model, because the model can learn unsupervisedly to improve its intelligence in modeling different data in different models, right? So that's why it's called bimodal modeling. So in order to collect these data, we did our best to go outside, on the internet to find as many data as possible about text and code about the specific programming library we want to support. So we went to Stack Overflow, Github, textbook, and web pages, a lot of different places, And we ended up with 50,000 code examples, 90 million words in text corpus, and then to bridge the gap between natural language and code, we use the API documentation because it has natural language description for each code entry, right? Either function or parameter or preference. So now there comes the most exciting part of this talk. It's opening up this black box. And it looks like this. It's a bimodal embedding. And sadly, I have to tell you that this only like opens 10% up of the black box. It's still 9% black, right? In terms of how we understand the training mechanism. But it's good enough for now. And let's see. So in order to understand this model, it is important to understand how do we map raw code content to this part. What is this part? This is a lookup table. This is like like a dictionary where there are certain entries. So how do we map a piece of code into entries on dictionary? And same here, how do we map a natural language query to entries on the dictionary? And then how do we map the model's output to the UI, right? So there are three things we want to solve. The first thing is how do we map a raw code to entries? Well, all code has some kind of structure, and in this case, it's a tree. If you are from CS background, you know that these are like abstract syntax trees, right? So, and each tree has a root. So we go from the root down to all the available paths, right? And then these are the different possible available paths, and then we count these paths over all the code examples we have collected, so that we can build up a dictionary here. And then the next time we see a new source code, we know how to map to the different entries on the dictionary. So that's how we solve the first problem. And how do we solve the second problem? This natural language, right? So the user has set face color of the bounding box. So we use traditional natural language processing method called bag of words, where we break the sentence up to different words. And naturally we have a vocabulary or a dictionary that we can have different entries mapped on the dictionary, and that naturally maps to that part of the neural network model. But there's a problem, because this is like when the model is deployed in the actual system, we know that what natural language query is. But during training, we don't know for a piece of code what natural language queries are, right? So like given this code, we don't know. So that's why we use API documentation to find the natural language captions for each piece of code, like functions and parameters, and we call them simulated natural language query when the model is being trained. And the same thing goes here. So let's look at the third problem. How do we map the network's output to user interface? Well, the network output is, again, this is like a code dictionary with different entries. And the model is actually not generating like one single prediction. It's more like generating a distribution over all possible entries on the dictionary. So this creates a challenging problem of how do we design the UI to make it effectively convey the user that what distribution it is like without confusing the user a lot, right? So we took inspiration from this design. So if you use Mac, you will be familiar. If you use Windows, maybe not. This is kind of like spotlight search, where the user can enter a query, and then sometimes the query may be ambiguous, and there like maybe multiple different parts are like highlighted, and this sort of solves the problem of ambiguity, right? So it's not like giving you one item; it's kind of like giving you a distribution. So we took that idea, but the problem is we have so many entries. Like there are tens of thousands of entries in this dictionary. We cannot show tens of thousands of items here. So we have to leverage the hierarchical structure of that again. So some of them are functions, some of them are parameters, some of them are values, and we use the hierarchical structure to make sure that this whole thing is like conveniently presented. So that's like the nested layer spotlight search that we proposed, where the top layer is function, second layer is parameters, third layer is values, and the user can click on these to navigate to the element he or she wants, and then the change will backpropagate to the top layer so that the change is applied. Okay, so finally, how well this whole thing work, right? We want to evaluate this. And we want to evaluate two parts. One is how well does the model itself work, and how well does the model plus interface, that means the end-to-end system, work. And for the first part, how well does the model work, we want to measure, can the model always give the correct suggestions? Design is a sort of information retrieval style evaluation. What that means is that instead of measuring accuracy, we are measuring the rank. So the input is code context natural language query, and output is code suggestion. So this is how we designed the study, the experiment. So we collect pairs of images. No, we collect queries using Amazon Mechanical Turk. We present Turkers with these image pairs. You know, this is before, this is after. How do you describe in natural language what is the change of this from this, right? And the Turker provide answers like change the color. Some Turkers provide some nonsense queries like the image is changed, which is useless, and so we dump these queries. So in the end, we collected 300 something valid questions, and 50 workers contribute to the study. So here's the result. We, like I said, we are evaluating the rank. So we use commonly used information retrieval ranking measurement, which is mean reciprocal rank. And what this means is that on average, the expected output, the expected suggestion, is ranked at the 4th place. So it's the inverse of this. So that's pretty good. And the other takeaways are the best performance is achieved by combining natural language context and code context. And if you take away code context, the performance drops. Or if you take away natural language context, the performance also drops. So that's the result of the first experiment. The result of the second experiment is that, the purpose of the second experiment is that how well the system works. In this experiment, we want to measure, can the system really help the user complete a task faster? And in order to do this experiment, we use the design format of a lab user study, where we ask the user, we give the user, hey, here's a piece of code. It generates this image. Can you change it using our system, or like a control group system, to generate this image, right? And the expectation is that the user can perform the code changes as fast as possible. And here, again, here are the two conditions. Here's the interface, and condition one is user can use our system or Google. It hasn't been shown on here, but there are like Google search results here in the actual user study. And the control condition is that user can only see the Google results there. All right, and then here is our example pair of images where we show how we show the user. And here are the results. So on average, we found that the condition one, the average task completion time is 108 seconds, which is lower than condition two with Google only 134 seconds. So that means on average, users using our system is faster than not using our system, not using CodeMend mechanism. And what else is that 70% of users in the post-study survey agree that this system efficiently helps me with solving my assigned tasks. So we think it's a good indication that overall the user likes the system. So we also want to dig deeper into how the user perceives the usability of the system. So we also ask them to provide any kind of feedback. And this is like one very representative, stereotypical thinking of, idea of our system. So this user says, I like it that it provides a comprehensive array of commonly used parameters to functions. That's something that Google doesn't or can't do, and it is helpful. So we think overall it is very positive that this is good. So that's current system. It still has a lot of limitations and can be improved greatly. So for future directions, we want to identify some usability issues in terms of how to support this and extend it to a lot of different other API libraries. How do we find a better representation that can encode the hierarchical structure? Nowadays, now in the model, we are only like flattening out everything. How do we actually encode hierarchical structure in code and natural language? And third, how do we find a way to extract the associations between natural language code? Now we just use API documentation library, but it is very limited. Sometimes we use the API function. not because of the surface meaning described in the documentation, but maybe because of some deeper semantic relations. And lastly, how do we find a way to encode API knowledge? And that's like encoding knowledge is a more general problem of deep learning, and it's going to take a lot of time for the field to explore. So in summary, we have introduced a system that shows that a neural network model can indeed improve the user experience of programming, so-called programming experience. And to train such models, massive text and code data from the web can be crawled and leveraged. And we designed a special user interface for that model so that we can further improve users' productivity. That's it. Yeah, thank you. Yeah.
So there's a lot of really bad code out on the internet.
Yeah.
How do you weight code that should be preferred, sort of stylistically good code or stylistically better code than do you have any?
Well, there are bad code, there are good code, right? And similar things like when Google machine translation is trained on a lot of bilingual text opera, there are bad translations, there are good translations. Overall, this thing will be smoothed out, and we just trust that overall the quality is good. And also, when we train the model, the code examples are filtered by whether they will be executed and compiled and executed correctly. For those that cannot be done so, we just throw them out. So that's some kind of filtering. Maybe there are other filtering mechanisms make this whole process better. I don't know. Maybe there's some space for improvement. Yeah.
How familiar does the person need to be with, I guess, the underlying task, and in order to use the language that's required to find, the appropriate function or.
That's a sort of a second layer of the question we're addressing. So if you don't know what you're doing, then if you don't know that you want to create a bar chart, then I'm not sure the system will help you. The user has to have some sense that what he or she is creating, right? What he or she is changing. So that area is second layer that we are not addressing in the scope of this study. Yes?
The system as it exists now, is it addressing only a single language, a single API set?
Yes. But we believe this kind of thinking, this idea design pattern is applicable or extendable to all kinds of programming. But in the future, we don't know nowadays.
Other questions? Right. Our speaker again.
Thank you.